Hey guys, welcome to graphical and numerical methods using Euler's method. Okay, so Euler's method is used to approximate a solution to a derivative equation y prime is equal to f of t comma y with initial condition y of t sub 0 equals y sub 0 with a fixed time step of h. So that might not make sense, but the idea here is if we have some curve, okay, whatever it is, we can estimate the value here of some point on that curve. And we're going to do that using what's called Euler's method. Now, this is a numerical approach to find an approximation of a value here. So a lot of this could be challenging for you at the beginning because you see a step of h, initial time or initial value here. But let's look at some examples, some concrete examples, just to show you what is going on here. So in example 1, we're going to let the derivative dy dx equal 3 over x. Remember, our differential equation. It says use Euler's method to approximate the y value with 4 steps starting at p sub 0 equals 1 comma 0 and letting delta x or h, okay, it can be either one, equal 0.5. So that's our step. So the first thing we're going to do is we're going to start with writing x sub 0. Well, our x sub 0 is this value. Here's x sub 0. Here is y sub 0. Okay, so x sub 0 equals 1. And it says we're going to go down to, so we're going to go out to 4. So we have x sub 1 equals, now that's going to be 1 plus your change in x, which is our h value, which is 0.5. Okay, so that's going to be 1.5. Okay, and we can continue on, and then it goes from 1.5. So the change in x is the same. So here's x2. That's going to be 1.5 plus 1/2. Okay, so that's going to make it 2. And that pattern continues. So we get x sub 3 is going to equal 2.5, and x sub 4 is going, x sub 4 is going to equal 3. Now, to get the y value, that's where you got to put a little work in. And so we're going to try to go straight across. We have y sub 0. They already told us what we're going to start with. It's 0. Okay. Now, here's where we're going to really kind of use that general pattern. Okay, so the idea here is if you want like y sub 1, you're going to have to use the previous term, y sub n minus 1, plus your change in x times your f of xy. Now that big F of xy might be confusing, but it's pretty easy to do. So let's look at y sub 1. Okay, so what we're going to do here is y sub 1 is going to equal y sub 0, the previous term, plus 0.5, and we haven't used that equation yet. So now we're going to plug in our two previous values. So 3 over x, there's just the previous x term. So this is going to be x sub 0, so we're going to plug in 3 over x. Okay, so what's in parentheses is we're just evaluating our function for x and y here. Okay, and that should be it, and then we're going to end up with 1.5. So that's our y1 value, but we want to see what the fourth value is. So y sub 2 now, we're using previous values, so we're going to take instead, we're going to have 1.5, there's your previous term for y, plus the 0.5 stays the same. And now instead of using 1, we've already used this one, we're going to go down to use 1.5, so it's going to be 3 divided by 1.5. Okay, and I put this into the calculator, I get 2.5 here. Okay, and then y sub 3, you're going to use the previous y term, which is 2.5, plus 0.5, okay, times 3. Now I've already used this x term, so now I use the previous term. If I'm on third term for y, I'm looking at the second term for x. That's 3 over 2. Okay, I multiply that out, I get 3.25. Okay, and my y sub 4 value now is going to be my y sub 3, which is 3.25 plus 0.5. Okay, times 3 divided by, well, I've already used this one, so it's 2.5. 3 divided by 2.5, I divide that out. Okay, so I get 3.85. So there's the estimation of y, in this case y sub 4, using Euler's method. Okay, so let's look at a couple more examples. Consider y prime is equal to y squared minus xy. Let y of x be the solution through y. Y of 0 equals -1. Estimate y of 1 using Euler's method, and a step size of delta x is going to be 0.5. So again, I'm going to start with x sub 0. Okay, x sub 0 is 0. We got that from looking right here. There's our initial condition, they call it. Okay, so that means x sub 1 is just a step increase, so that's going to be 0 plus half. This is 1/2. Okay, and x sub 2 is going to be 1. Now remember, this is just using your previous term, x sub 0 plus your change in x. So this is then x sub n minus 1, the previous term, plus 0.5. That's how we're getting those here. I was going to switch colors, but it didn't quite work out. There we go. So that's how we get, that's just the formula to get those other two terms there, x1 and x2. So let's look at finding the y values here. So y sub 0, the initial condition is -1. Okay, so let's use our formula now. So you're going to have the next term, which is y sub 1. And that's going to be equal to -1 plus your 0.5, your change in x, times f of xy, which now you have to plug both x and y in. So if we're looking for y sub 1, we have to use x sub 0 and y sub 0. So it's basically you're going to have our y value squared. So y squared, which is now our y value was -1, that's our original, squared, minus x times y. Our x value, x sub 0, is 0, so that whole second term is going to cancel, times -1. Okay, and then we'll close that off, and we get, when we go ahead and do that, I get -0.5 when I multiply all that out. If we want to go one more, so estimate y sub 2. So there's our estimation. Whoops. There's our estimation of y sub 1 right here. I'll do one more just for fun. You could take the previous y term, so it's -0.5. Okay, plus the change in x times, now we would plug in our y1 and x1 values. So our y1 value here was -0.5 squared, minus x sub 1, which was 1/2, so 0.5. A lot of 0.5s here, right? And then times the x value, which was -0.5. Okay, and if you multiply all this out, you get -0.25. Okay, so we can multiply. I just want to show you a couple steps on the Euler's method. I do have one more example. And this one, given that y sub 1 equals -3 and the dy dx equation equals 2x plus y, what is the approximation for y of 2 if Euler's method is used with a step size of 0.5 starting at x equals 1? So I've used this one a lot, that delta h. It's pretty common to use that one. So again, we start with our x values. So I'm just going to go x sub 0, which in this case they tell me is 1. Now my change is half, so the second point is going to be 1.5, okay, and x of 2 is equal to 2. Okay, so I like to split this. I have been. So y sub 0, okay, x was 1, so you matched here, and then y sub 0 is -3. So now to get y sub 1, I take my previous y value, I'm going to add to that the quantity, my change in x, times the evaluation of my function 2x plus y. So my original x was 1, so it's going to be 2 times 1 plus my y value. My y value here is -3. So I go ahead and plug all that in, and I end up with -3.5. I need y sub 2 though, so I got to go one more, and I'll use my previous y term, -3.5, plus the step increase or step change, excuse me, and then it's going to be 2 times, not 1, it's going to be 1.5 minus my y value. My y value is negative 3.5, so it's going to be, plus y, so it's going to be minus 3.5. Close that off, and when I estimate that, I get approximately negative 3.75. Okay, so that is Euler's method, using Euler's method to find the estimation of a value along a derivative curve or a solution curve. So if you guys have any questions or comments, let me know, and we'll see you next time.